Hello everyone and welcome back to another video here on the channel. I'm your host Void, and as I mentioned last video, I am working on things that are not related to Minecraft, but since my whole channel and even my channel name is based around Minecraft, I thought it would be foolish to sort of diverge away from that. So what I thought I would do is try to pick out subjects that I'm interested in outside of Minecraft, which usually revolve around maths or science, in this case maths, and somehow tie it back in to Minecraft and tech and all the stuff that I enjoy doing in Minecraft. So today I thought I would share with you how to plot the Mandelbrot set in Minecraft. Now, the Mandelbrot set, and I have relevant articles and whatnot down in the description below. The Mandelbrot set is a fractal. It's an infinite pattern that you can zoom into, and it will have increasing levels of intricacy as you go through. And I'll explain kind of all of that a bit later on. But let's get into how to actually plot the Mandelbrot set normally, not in Minecraft, and I'll show you how to do it in Minecraft. So you start out with axes. Now, the x-axis is fairly normal. It's got the real numbers in there, so you've got 0, and then it goes up positive and down in negative. Now, the y-axis is a bit different. The y-axis is multiples of the imaginary number, I. Now, you can express every number on the x-axis as a multiple of the square root of 1, which is of course 1. So if you do, for example, 2 square root 1, then that will be the same as 2, because the square root of 1 is 1, 2 times 1 is 2. Now, imaginary numbers are multiples of the square root of negative 1. Square root of negative 1 is I, so 2 square root of negative 1 will be 2i, 3i, 4i, etc, etc. And because we don't know what the square root of negative 1 is, then it's just expressed as I. It's not written as a legitimate number or a decimal or anything like that. It's just written as I. Now, this looks pretty similar to a graph. You've got the x-axis and you've got the y-axis, and they have numbers on them. So if you join 2 points together, you can locate a point on the graph. Now, normally that would just be a set of coordinates, but in this case, because we're combining a real number with an imaginary number, it turns into a complex number. So in this case, this is negative 3 and 4i. When they combine together, they create the complex number negative 3 plus 4i, which of course is undefined, so we just leave it as it is. To work out if a point is indeed on the Mandelbrot set, we have to use a function, which sounds quite scary to a lot of people, but it's really just running the same equation over and over and over again. We're using the function z equals z squared plus c, where z starts out as 0 and c is the real number component of your complex number. In this case, we want to find out if 1 plus 0i is a point on the Mandelbrot set. So we're looking at 1 as the real number here. Z always starts out as 0 in iterative functions, which is this one. So if we substitute z for 0, then we've got 0 squared plus 1 equals 1. And that is the function of z. Now, because it's iterative, you then plug this result, which is of course 1, back into the function, like so. So you've got z equals 1 squared plus 1 equals 2. And the more times you run this, the more you'll notice it just gets really, really big, really, really quickly. So this point is not on the Mandelbrot set. On a typical graph, you'll probably mark it with a particular colour that indicates that it is not on the Mandelbrot set. It really doesn't kind of matter what colour it is, as long as it's not the same colour as anything else. So the complex number 1 plus 0i is not a point on the Mandelbrot set. Let's look at another example. So there's our function again, function of z equals z squared plus c, and z always starts out with 0 in iterative functions. Let's look at -1 plus 0i as an example. Just make the real number negative, it's pretty easy. So in this case we're looking at z being replaced with 0, so function of z equals 0 squared plus -1, which is of course -1. 0 multiplied by 0 is, funnily enough, 0. Then you plug -1 back into z, so you end up with the function of z equals -1 squared plus -1. -1 times -1 is +1, and this just goes straight back to 0. And the more you do this, the more you'll notice it just alternates between -1 and 0. It just goes back and forth over and over and over again, which means this point is in the Mandelbrot set. I mean, you've got a rather intense shade of green there. I apologise for that. I'll probably put like epilepsy warnings or something on screen at the beginning. That's very intense. Should have changed that. My bad. This means that the complex number -1 plus 0i is on the Mandelbrot set. Let's look at the example that I had in the very beginning to show you what a complex number is. So there's our function again. It's become rather familiar now. Function of z equals z squared plus c. Z always starts as 0 in iterative functions, and our complex number in this case is -3 plus 4i. Start out with substituting z for 0 and c for the real number component in our complex number. And it sounds complicated, but there's just loads of terms, loads of ways of saying things that are chucked around. I suggest you go back, if you're confused, you go back through the explanation to make sure it's fresh in your mind again. So in this case we're doing 0 squared plus -3. Of course that comes to -3 again. Then we do the same thing, so we plug -3 in as z. Function of z equals -3 squared, which is 9, +9, plus -3, and that gives you 6, because adding a negative number is the same as subtracting the positive counterpart. Plug the 6 back in, and you get 6 squared, which is 36, plus -3 is 33, and this clearly gets really big really quickly, even bigger than the first example I showed you, which means this point is not in the Mandelbrot set. Complex number -3 plus 4i is not in the Mandelbrot set, and the reason why you see loads of beautiful colours, I personally love looking at the Mandelbrot set and the zooms and things that people have made, because people assign different colours to different what we call magnitudes. So for those equations that I showed you, they get bigger, they spiral away to infinity at different rates. So the second example I showed you was on the Mandelbrot set. That was the complex number -1 plus 0i. So you'd mark that as the colour of your Mandelbrot set itself. But the first example, you'll mark it a different colour to the -3 plus 4i, for instance, just to give an extra level of intricacy. You could just have two different colours, one that are in and one that are not, but it's an excuse to make something look a lot nicer, which in my opinion should always be taken. Now, the Mandelbrot set looks really big and looks like it might appear, I don't know, from -10 to +10 or something, but that's only because we're zoomed in really far. It actually only appears about there, between about -1.5 to +1.3, it looks to be. So it is really small, so you can kind of, if you want, sort of knock from 2 upwards off on all sides, just to make it a bit simpler for you, because you would be plotting decimals as well. For example, if you wanted to, I don't know, find if the point on what we now know is the very end of the Mandelbrot set, you'd have -1.5 plus, I don't know, say 0.5i, which really just sounds completely bonkers and very difficult to work out. But you can just use a calculator. It's in fact, you don't even need a scientific calculator to be able to do iterative functions. You just quite literally put the result back in as it stands, and if it spirals away to infinity very quickly, then mark it as one colour, not so quickly another colour, not at all, kind of alternates between 2 different numbers. It is in the Mandelbrot set. Now, some extra bits of information. The area of the Mandelbrot set is currently unknown, but is estimated to be about 1.506591884 square units plus 0.0000000028, give or take. But its perimeter is infinite. And it might not look infinite just by kind of observing it, but you have to take into account the coastline paradox. Now, this line on screen now looks really kind of straight and, you know, nothing really too different about it. But if we zoom in, we'll notice that it has a staircase effect. Now, zoomed out, you could probably measure it on the screen to be, I don't know how big your screen is, probably not very big. On my computer screen, it's I'd imagine 1.5, couple of inches, whereas this one, you'd take into account every step, every staircase across and down, it's going to be a lot longer. And if you have an infinitely intricate pattern like the Mandelbrot set, there is no possible way to zoom in to a complete level of accuracy like I have here with the staircase. So the more you zoom in, the more you'll notice all of the sides are just going to be more and more swirly or jagged or not smooth. So it's completely impossible to measure it, and it is an infinite perimeter. Let's take all of this information. It was a lot, so I suggest replaying it and watching some videos that I link down in the description and reading some articles that I've also linked down in the description. Let's take all this information and let's go to Minecraft. So I am inside of Minecraft, stumbling over my words, as I said just a second ago I would be. So I've made some axes here, very rudimentary axes signs, because I believe that if you're even attempting at trying to plot the Mandelbrot set in Minecraft, you need to have some sort of reference as to where you are. For example, if you're plotting this space here, and you know that it's point -2 plus or minus 8i, because otherwise you're just going to be completely lost. So lay out your axes, and you actually don't want it from 0 to 8 on every end, because as I mentioned, the Mandelbrot set actually kind of only appears from -2 to +2 on X and Y. So just get rid of the signs that you don't need, like this. And then depending on how big of an area you want, Mandelbrot sets would look amazing as a floor of a perimeter. So you could do that. Just kind of expand these axes. So you might want to have 0 here, and then 2 over here, and you'll move this there, and 1 here maybe, and then sort of fill it in like this. And don't be afraid to use decimals, because I mean, really, decimals are kind of what make the Mandelbrot set as defined and as intricate as it is. Yeah, don't be afraid. I mean, I would be lying if I was saying that, you know, you could do this. This would be really quick, and do it with some friends over an afternoon or something. No, it will probably take a number of months at the very least, maybe even like half a year or even a year to make like a perimeter or something. It's not going to be quick. Now, you could develop some code or something that where you can enter in a complex number and it will work it out itself. But even then, you know, doing that for 9x9 chunk perimeter, 20,736 separate calculations that you'd have to run. 20,736. Make that 21,000, just to make the number sound even more extravagant. That would take you forever, even with a Python script or something. I mean, a project like that wouldn't be for the faint-hearted, but you just watch back the video that I played to you, or one of the videos in the description, whichever one helps you the most. You know, I'm not going to be offended. And use the iterative functions to find out whether, say, complex number -1.5 minus 0.3i is in the Mandelbrot set, and you're well in your way. Now, of course, you wouldn't be able to create an infinite pattern in Minecraft, because blocks are limited to 1 meter by 1 meter by 1 meter. But you can definitely go down to a very sort of precise extent, so you can see the beautiful cardioid shape and all of the lovely bits on the outsides, and make it look good that way. So unfortunately, that's all I've got time for today. Thank you so much for watching. This is, as I mentioned, a very different video, and I really enjoyed doing this. Actually, I might consider doing similar things. So I bring science and mathematics and psychology and other things that I have a huge passion for, sort of tie it into Minecraft as tightly as possible, so that I can get your attention, keep my focus, and overall make it a great series. So let me know your thoughts and whatever, especially for these sorts of videos. All relevant links will be in the description below, because they can get very sort of heavy with information, and I'll also put anything which sort of inspired me to do this, like people who have plotted the Mandelbrot set before, and so on. Just things like that. Just definitely check the description because there's everything down there. Thank you so much for watching, and I will see you all in the next video. Bye bye.